This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on the end behavior of polynomials. So let's look at y equals x squared. That's a parabola. We know the general shape of y equals x squared. So looking at the graph, we see this parabola. Now, what is the end behavior? As x gets large, the y values get large. As x gets large negative, the y values get large positive. So we're going to need to have a way to describe that behavior. And what we say is, as x approaches infinity, y is approaching positive infinity. As x approaches negative infinity, y approaches negative infinity. Now how does that change if we change the coefficient? So right now this is y equals positive 1x squared. What if I had y equals negative 1x squared? So we can probably visualize that graph, an upside down U. So let's see it. Indeed, that's what it looks like. And then how do we describe its end behavior? As x goes to positive infinity, what's happening to y? It's going to negative infinity. As x goes to negative infinity, what's happening to y? It's also going to negative infinity. So we describe the end behavior of y equals negative x squared that way. Now what will be nice about these two graphs is they will tell us something about all polynomials whose highest power is even. 2 is an even number. So focus on the highest power of the polynomials, identify if it's even or odd, and then look at the coefficients. That'll be the strategy we're going to use to determine the end behavior of any polynomial. So next we have y equals x cubed. Notice that's an odd power. Hopefully you have that image in mind. Looks something like that. And there's our picture. So how would we describe the end behavior here? As x gets large positive, y gets large positive. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y would also go to negative infinity. So down to the left, up to the right. And there's our way of describing that. So this is an odd power with a positive coefficient. Things are going to behave that way. Now I could have just said y equals x to the first. Y equals x to the first is a line through the origin with a positive slope. So notice for x to the first, a problem with an odd exponent with a positive coefficient. Notice this end behavior is the same. Well, let's go ahead and take negative x cubed. What will that look like? So we think of the behavior looking this way. So it should go up to the left and down to the right, and indeed, that's what we have. We want to go ahead and express that end behavior using this sort of notation. So as x goes to positive infinity, y should go to negative infinity, and it does. As x goes to negative infinity, y should go to positive infinity. So we're going to keep these ideas in mind. We have the x squared version and we have the x cubed version. They're going to be reminders of the behaviors for functions with either even powers or odd powers. So we're going to first look at even powers. So we have y equals 2x to the fourth minus 5x cubed minus 7x squared plus 3x plus 1. Even power, x to the fourth. So we're going to think about how the x squared graphs look. Positive coefficient. That's going to make us think about the y equals positive x squared graph. The end behavior will be the same. So sure enough, highest power is even, leading coefficient is positive, so the end behavior will be like y equals x squared. Well, what was y equals x squared? As x was large positive, y was large positive. If x was large negative, y was large negative. Because we're visualizing that u. All right? A positive x squared is a u. Now looking at this actual graph, does it satisfy that condition? Do we see the end behavior when we examine the graph? Sure enough. X goes to positive infinity, y gets very, very large. X goes to negative infinity, y gets very, very large. So the end behavior of this is like the u. Now notice the intermediate behavior is going to change. It's going up and down, up and down. All kinds of crazy things can happen in between. But at the far tails of the graph, it will behave like the y equals x squared because highest power is even with a positive coefficient. Now with our next example, the highest power is still even. So we're thinking of the x squared and the negative x squared graph. But the coefficient this time is negative 1. So it's an even graph with a negative exponent, so it's an upside down u. So we know that it should have the same general features as negative x squared. So as I'm writing here, highest power is even, leading coefficient is negative. The end behavior will be like y equals negative x squared, upside down. So in each case, with an upside down u, as x gets large, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. And we can see that that's the information we have here. Now looking at the graph, do we see that behavior? Sure enough, down to the left, going to negative infinity as x goes to negative infinity. Down to the right, as x goes to positive infinity, y goes to negative infinity. So this is behaving like negative x squared. It's behaving like the upside down u. Notice it's bouncing around a little bit in the middle, and behavior tells us nothing about what happens in the middle, and behavior just what happens in the tails of the graph. Okay, let's move on to odd powers. So now we have 2x to the fifth minus x to the fourth plus 4x cubed minus 3x squared plus 5x plus 2. Odd power, so we're going to think of x cubed and negative x cubed. Coefficient is positive, so therefore it should have the same shape as y equals x cubed, which looks something like this, down to the left and up to the right. So we'll go ahead and state it formally. Highest power is odd, highest power is x to the fifth. Leading coefficient is positive, in fact it's positive 2. So the end behavior should be like x cubed. So as x goes to infinity, y should get large. As x goes to negative infinity, y should get large negative. And looking at the graph, does it fit that pattern? Sure enough, it does. This looks very much like y equals x cubed. There's not a whole lot of bouncing around in the middle. That depends on the coefficients on the inside. But certainly down to the left, so as x goes to negative infinity, y goes to negative infinity. Up to the right, as x goes to infinity, y goes to infinity. Because this is behaving like x cubed, odd power, positive coefficient. What about this one? Y equals negative x to the fifth minus x to the fourth plus 3x cubed minus 2x squared plus x plus 2. Highest power is odd, coefficient is negative. So we're going to think of the graph of negative x cubed, which is going to look like this. Up to the left, down to the right. We'll state it formally. Highest power is odd, leading coefficient is negative. In fact, it's negative 1. So the end behavior will be like y equals negative x cubed. And again, have the visual in mind, up to the left, down to the right. So as x goes to negative infinity, y goes to positive infinity. But as x goes to positive infinity, y should go to negative infinity. Which is what we have. As x goes to positive infinity, we have a situation where y is going to negative infinity. Where x is going to negative infinity, we have y going to positive infinity. Does the graph support that? Sure does. We have some bouncing around kind of stuff in between. But as x goes to negative infinity, y is getting large positive. As x goes to positive infinity, y is getting large negative. So you look for the highest power. If it's even, it's like an x squared. If it's odd, it's like an x cubed. And then you look at the sign to see if it's positive x squared, negative x squared, positive x cubed, negative x cubed. So if you have those 4 graphs in mind, it's relatively easy to determine the end behavior of these functions. Now, here's a polynomial that's not all multiplied out. So we have to ask ourselves, if you would multiply all this out, what would you get? Well, you get an x to the first here, an x squared here, an x squared here. The total would be x to the fifth. So this is going to be a polynomial whose highest power is odd. And our coefficient, if you multiply this all out, x minus 1 times x plus 2 times x plus 2 times x minus 4 times x minus 4. The leading coefficient is just going to be 1. So we have a total of x to the fifth in our powers. Leading coefficient is 1. Odd, positive is the model we're going to look for here. So if we're odd positive, highest power would be 5, multiplying this out. Leading coefficient would be positive 1. So this is going to behave like x cubed, down to the left, up to the right. So formalizing that, what do we say? As x goes to positive infinity, y goes to positive infinity, up to the right. As x goes to negative infinity, y goes to negative infinity, down to the left. Looking at this graph, do we see that? We sure do. Notice lots of bouncing around here. We can also notice we have some zeros. X minus 4, so 4 is a 0 here. X minus 1, 1 is a 0 there. X plus 2, negative 2 is a 0 here. Not labeled on the graph, but you can see where those are. And you can also see that negative 2 is bouncing. So that 0 is got multiplicity 2, so it bounces. X minus 4 has multiplicity 2, so it bounces. But this lesson is on end behavior. As x goes to infinity, does y go to positive infinity? Sure does. As x goes to negative infinity, does y go to negative infinity? It sure does. So this problem, even though it's not multiplied out, follows the same general pattern as the other ones we've looked at. Okay, now how about this one? Y equals negative 3 times x minus 5 times x minus 2 squared times x plus 1 cubed. Ignoring the negative 3 for a minute, multiplying all this out, x to the third, x to the second, x to the first, that would give me x to the sixth. X to the sixth, multiplying all these x, multiplying this stuff out would just give me a coefficient of 1. But when I multiply that by negative 3, I get a coefficient of negative 3. 3, 4, 5, 6, even power. Leading coefficient is negative 3, is negative. So we know it's going to be an even negative. It's going to behave like negative x squared, which is what we're saying here. Even though negative 3x to the sixth would be our leading term, since it's even and negative, we know it's going to behave like that. That is an upside down u. So in both cases, the y values will go to negative infinity. So we say as x goes to infinity, y goes to negative infinity, and then as x goes to negative infinity, y goes to negative infinity. So if we look at the graph, do we see that end behavior? And you'll notice, to get a decent graph, my range of y's is well over 1,000 up here and down to 2,000 here. Yet on the x values, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3. So if you're going to graph this to check, you've got to make sure your window is large enough to see that end behavior. But sure enough, this graph behaves like negative x squared, down to the left and down to the right. And that will conclude this lesson.